fine. I hope. Yeah. No problem, no problem.
Ok. Hola, buenos días a todos. Vamos a ver, intentaré hablar en inglés para que este hombre, pues, los que no hablan español, pues entiendan. As you probably know, this year, the Japanese Institute have installed a telescope, a microwave telescope, in the observatory, Teide Observatory. It's a small telescope, 2 meters more or less, but it's very interesting telescope, a very different telescope. The name is a bit difficult. Shunsuke. Onda. The second part is very easy. It's one of the component of this group. He finished the bachelor degree at 2014, later the master in 15, and the PhD at 18, more or less. Very young people. After that, you have now is doing the postdoctoral in Kyoto University. And the project you are, digamos, works is about CMB, with B-mode polarization using, of course, this telescope, the GroundBIRD. To finish, I like to say that it has been very nice work with this group and with this men. Thank you very much. You can start.
Okay, thank you very much. So today I will talk about the GroundBIRD experiment, the observation of the CMB polarization with wide sky survey and fast rotation scanning technologies. So my name is Shunsuke Honda. So it's difficult for you, but yes. So on behalf of the GroundBIRD collaborations. So at first, I would like to introduce some motivation in our experiment, and I briefly introduce some specification of our telescope. And then I show some highlights, some results in Japan and also in the observatory. Okay. Then the CMB is a cosmic microwave background radiation. We can see anywhere that come from the 2.7 Kelvin. And then our experiment motivation is to get the evidence of the inflation theory. In this theory, the time and space was exponentially expanded at the beginning of the universe. And then in that time, due to the exponential expansion of the space, the primordial gravitational wave was generated. So as you know, the gravitational wave generally don't interact any other particles, but the CMB can be affected by this primordial gravitational wave, and some special pattern on the CMB polarization map. So that pattern we call the B-mode polarizations. And normally, the CMB can be polarized by the interaction of the electrons. So this is the E-mode polarization we call. And then, So then we can measure the CMB polarizations and make some map. And after that, if we make some power spectrum in terms of the multiple moment, the space frequency, the x-axis shows the multiple moment, and the lower multiple moment, meaning the large angular scale, that means the something like a 2-point correlation from each other. And then if we want to see the large multiple moment, that means the 2-point correlation with the 2 points are very close. And this color lines shows the B mode spectrum generated by the primordial gravitational wave. And then we have some bumps here and here. And here, this bump was generated in the recombination era of the cosmos in the history of the universe. And this bump was generated in the deionization era. So to evident that we got the B mode spectrum by primordial gravitational wave, it is good to get both bumps at the same time. And then I show the dotted line. This is the E mode spectrum. So actually, the E mode spectrum is much larger than the B mode spectrum. So then we have to do the precise measurement to detect the B mode polarization spectrum. So, okay. Okay, and then our experiment, GroundBIRD experiment, realized it to get both bumps and enough sensitive to detect the B mode spectrum with wide sky observation with rapid rotation scanning. So our telescope is like this, a relatively small telescope than other experiment, but the telescope is for the precise observation for CMB polarization with unique technologies shown here. The telescope is, of course, installed in the Teide Observatory. And at first, we measure the CMB polarization with elevation fixed to the 6 degree. And the beam resolution is about 0.5 degree at CMB frequency, 145 gigahertz. And to maximize the sensitivity, we utilized the superconducting detector named MKIDs. The MKIDs has a good time response other than the other superconducting detector like TESS or something. And most interesting point of this telescope is the rotation speed. That speed is 120 degrees per second, so meaning the 3 seconds for one rotation. Generally, that kind of telescope can rotate only 1 minute for one rotation or something. So then they're much faster than the other experiments. So this speed can mitigate the effects of the atmospheric fluctuations. So in the CMB polarization experiment on the Earth can be limited by the atmospheric fluctuations. So then we have to increase the rotation speed to get the sensitivity for the wide sky observations. And when we set the elevation at the 60 degree and we rotate, we can measure the data like this. And then because of the Earth's rotation, we can measure about 40% of the full sky. And inside of the telescope, we have a Cryostat for the superconducting detectors. And we are using the two kinds of the Cryostat. One is the PTC cooler for cooling down to 4 Kelvin with 3 thermal shields as shown, sky blue, blue, and this one. And inside the 4 Kelvin shield, we have a cold optics with cross-dragon mirror to reduce the thermal noise at the deflections. And then we install the sorption cooler inside the 4K shield to cool down to the 250 millikelvin for the superconducting detectors. And the detector is installed in the focal plane with the several bandpass filters. And then the most important issue is the rotation system in our telescope. So actually the PTC, as shown here in this picture, PTC requires the high pressure helium gas from outside. So then we have to connect 2 lines for helium, as shown here. And then the compressor, which generates the high pressure gas, is very heavy and very large. So then we cannot install the compressor on the rotation tables. So then we have to set on the ground. And if we connect the helium lines directly compressor to PTC, and we can start rotate, the helium lines are twisted and broken. So then we install the rotary joint with this point. So the schematic is shown here, and the green one is the rotary joint for the helium line and also one electrical power. And this is a rotation table, and the green one rotates with the rotation table. And yellow one is fixed to the ground. And then, so we have some hole with the donut-shaped hole here. And then we can connect the helium line here. So then if this rotary joint rotates, the helium line can always connect it to the PTC. So that's why we can get the helium lines between PTC on the rotation table and compressor fixed on the ground. And also we can install the one line for electric power. This can be connected to the commercial rotary connectors. And then we can successfully rotate 20 RPM, meaning that 120 degrees per second, with cooling down to 250 millikelvin for detectors. And for that rotation, there are almost no vibrations and works well for now. And also, of course, we can rotate continuously forever. So then it's a very good technology to realize our experiment. And after cooling down to the lowest temperature, we can get the CMB signal by using the KID detectors. So the KID is a kinetic inductance detector. This is one kind of the superconducting resonators. So then with this kit, the kit has one resonance frequency like this. And then the kit is connected to the antenna and to feed lines to read out the data. And then when we monitor this kit property on these frequencies, and then the CMB signal injected to the antenna, the superconducting state will change by the injected energy. And then the resonance condition is also changed, as shown in the red dotted line. And then if we monitor the kit response with this frequency, the output voltage is changed like this. And this difference is corresponding to the injected signal. So then we can measure the CMB temperature or the CMB temperature of polarization with these detectors. And the most interesting point of the kit is the multiplexing. So we can connect a lot of kits in one field lines. So then, we can set the different resonance frequencies for each kit, and we can measure simultaneously all kits by introducing the multi-tone wave in one system. So I showed one example. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 resonance peak for M kits. And then if we inject the frequency 1, 2, 3, 4, 5, 6, 7, 8, we can get the data for each frequencies simultaneously. So that number of kits can be increased a few hundred or a few thousand in one field lines. So then in the CMB experiment, number of detectors is very important. So then the kit is very good to use in that experiment. And that detector is installed in the focal planes. This focal plane is relatively smaller than the other experiments, so the 40 centimeter by 20 centimeters. And in front of the focal plane, we install the bandpass filters at the 350 millikelvin. And then we can install 7 wafers at the same time, and 6 wafers for CMB observation with the 145 gigahertz, and 1 wafer for 220 gigahertz to understand the foreground for CMB and to subtract these foreground components from the CMB data. And I show one filter transmittance. Each dot line shows each filters, and then the black line shows the 145 gigahertz filter, and this black line shows the 220 gigahertz bandpass filters. And of course, we measure this filter property individually, and we have a good consistency between the design value and the actual data. Yes, and then after constructing all telescope components, we checked the telescope performance in Japan. So actually in Japan, we developed the telescope inside the building. So then we cannot see sky or moon, sun or something. So then, but we have one mercury lamp on the top of the building. So then we can see this mercury lamp in Japan. So when we set the good one elevation angle to see the mercury lamp, and then we can see some TOD data, and then we can see one peak with this mercury lamp for every rotation. In every rotation, one peak, one peak, one peak, one peak. And then we turned off the lamp. The signal height is decreasing as expected. And then we also have elevation scanning to get the beam size for that telescope. And the x-axis shows the elevation angle, and the y-axis shows the response of the kit when the kit sees the mercury lamp. the obtained the width is consistent to the size of lamp, mercury lamp, and the telescope beam. So then the mercury lamp response was successfully observed. And then we brought the telescope to the observatory. And we installed the GroundBIRD telescope next to the Kyoto building. And now we usually observe and monitor the telescope condition in this R1 house. And after bringing the telescope here, we reconstruct the Cryostat in the AIV room here. And we escape this, so we can successfully construct it. And then we install the rotation system at first in the observatory. And yeah, and so when we install the rotation system, we can check some leveling, something like this, and we can get the leveling for that rotary systems. And after that, we install the telescope itself, as here, here. And then we confirm the telescope can rotate 20 RPM, same as in Japan. Okay, and then the 21st of September last year, we successfully observed the first light by using the moon signal. And these are preliminary results. And I think this is a good figure. And this is the obtained moon images obtained by the GroundBIRD telescope. And the property is reasonably consistent to design value. So then we can do now more precise measurement by moon and also sky temperature or something. Okay, this is summary. So now we try to observe the CMB polarization with larger angular scale than the other experiment with unique technologies. The one is a high-speed rotation scanning at 20 RPM with the custom Rotary Joint, and the KID detectors on the focal plane. And the almost developments done in Japan, and now started observation in Teide Observatory. And in September, we got the first light successfully by using the moon. And now we are in the commissioning, and we will start physics observation as soon as possible. Okay, thank you very much.
Thank you very much. Can you show the first light slide, in the first light in Japan, where you
in Japan?
In Japan, yes,
okay.
The first slide in Japan. You show the mercury lamp over there. Well, I can see that when you switch off the mercury lamp, there is a huge. The response of the detector is still existing during a long time. I wonder whether this is an effect of the mercury lamp itself, or whether it is an effect of the MKIDs.
The property of the mercury lamp.
Okay.
Yes.
Thank you. Okay.
Thank you very much, Shunsuke, for your explanations. My question is concerning the Rotary Joint, because we have similar in Quixote, and we have in the past we were not able to found a rotary joint for helium because of the leaks of this kind of rotary joints. So my question is this a commercial article, or do you design specifically for your project?
The rotary joint is a custom one, made by Japanese company. So I think this is very yes.
So and it's
special one. Yes.
It's working very well with
Yes,
helium.
yes,
You
yes.
have no problem of leaks with helium. Okay.
No problems. Completely.
Thank you.
Hello. Can you tell us a little bit about the future plans? So now you are in the commissioning.
Yes.
When do you expect to finish the commissioning and start with the science observations?
We hope that we can start the physics observation in this year, but for now the first lighted commissioning is now done with the prototype detectors. So then in that detector there is not so many pixels. So then at first we have to upgrade the detectors, and the detector itself is now in development in Japan. So then I think we can start the physics observation in this year.
And can you upgrade the detectors at the observatory, or
In the observatory, yes.
in the observatory?
If the weather is good. Any more questions? Thank you.